This is a recast of the 6,300-word piece, Self-Organizing Maps, SOMs, from Schneepat.com. This article is about self-organizing maps, SOMs, which are neural network architectures used for data visualization, analysis, and clustering. SOMs employ unsupervised learning to map high-dimensional data onto a lower-dimensional grid, allowing for the extraction of patterns and relationships within the data. They have applications in various fields, including image processing, speech recognition, bioinformatics, and personalized marketing. However, they also have limitations, such as sensitivity to initial conditions and potential overfitting. Overall, SOMs are powerful tools for organizing and understanding complex data. Let's listen in.
Today, we're talking about self-organizing maps, or SOMs, which are a popular tool in the field of machine learning. SOMs were introduced by Tugo Kohonen in the 1980s and have since become widely used for data visualization and analysis.
That's right, Theo. SOMs are a type of neural network that employ unsupervised learning to map high-dimensional data onto a lower-dimensional grid. The algorithm behind SOMs iteratively adjusts the weights of the network to form clusters of similar data points on the grid, uncovering underlying patterns and relationships in the data.
Absolutely. The key idea behind SOMs is that similar data points are grouped together in the same cluster, while dissimilar data points are located far apart. This allows us to extract patterns and understand the relationships between data points.
Right. And SOMs consist of a two-dimensional grid of nodes, where each node represents a specific feature or region of the input data. These nodes are connected to their neighboring nodes through weighted connections, allowing them to learn and adapt based on the input data.
During the training phase, SOMs undergo an unsupervised learning process where they adjust the weights of their neurons based on the input patterns. This adjustment follows a competitive and cooperative mechanism, where each neuron competes with its neighboring neurons to win the right to represent a specific input pattern.
That's correct. The winning neuron and its neighbors then update their weights, gradually organizing themselves spatially to form a topological map that reflects the characteristics of the input data. This process allows SOMs to effectively visualize complex data and provide insights into its underlying structure.
And that's why SOMs are considered important in various applications. By reducing the complexity of high-dimensional datasets and mapping them onto a lower-dimensional grid, SOMs offer a visual representation that aids in understanding the underlying structures.
Absolutely. This is particularly crucial in fields such as data mining, where SOMs can be utilized for clustering and classification tasks. SOMs have also found applications in image processing, speech recognition, and data visualization, among others, making them versatile tools that contribute to advancements in various domains.
That's right. SOMs have the ability to uncover hidden relationships and patterns within large and complex datasets. Their ability to organize input data into a two-dimensional grid of neurons allows for a better understanding of the underlying structures.
And let's not forget about the history and development of SOMs. They were first introduced by Tugo Kohonen in the 1980s and have since gained popularity for their ability to visually represent complex datasets. Inspired by the principles of neural networks, SOMs mimic the organization and structure of the brain.
Definitely. The development of SOMs can be attributed to advancements in machine learning and computational modeling. Over time, various modifications and improvements have been made to SOMs, including enhanced topological mappings and adaptive learning rates, further expanding their applications in pattern recognition, data clustering, and visualization.
And that wraps up our discussion on self-organizing maps. We've learned how they work, why they're important in various applications, and their history and development.
Join us next time as we dive deeper into the applications of SOMs and explore real-life examples of how they have been used. Welcome back to our podcast. Today, we're going to dive into the world of self-organizing maps, also known as SOMs. These powerful neural network architectures were first proposed by Finnish professor Tugo Kohonen in the early 1980s. He was inspired by how the human brain processes and organizes information and aimed to create a computational model that emulates this ability.
Absolutely, Theo. Kohonen's research and contributions to the field of SOMs have been pivotal in the development and understanding of this data visualization and clustering technique. His work introduced the concept of SOMs and provided a framework for organizing high-dimensional data in a lower-dimensional space while preserving the underlying structure.
That's right. Kohonen's contributions extend beyond just SOMs. He has also greatly influenced our understanding of neural networks and their application to artificial intelligence. His work has had a significant impact on fields such as image processing, pattern recognition, and data mining, making him a pioneering figure in the field of unsupervised learning algorithms.
The development of SOM algorithms and techniques has seen significant advancements in recent years. One area of focus has been improving the learning process within SOMs. Researchers have proposed strategies like incorporating adaptive learning rates and introducing dynamic neighborhood functions. These approaches enable SOMs to adapt better to complex and high-dimensional datasets, resulting in more accurate clustering and visualization outcomes.
Absolutely. On top of that, efforts have also been made to optimize the computational efficiency of SOMs by developing parallel and distributed versions of the algorithm. These advancements have expanded the potential applications of SOMs and made them more accessible to a wider range of industries and domains.
Self-organizing maps offer a powerful tool for visualizing and understanding complex data patterns. By organizing data into a lower dimensional grid, SOMs allow users to explore and interpret data relationships. They can identify clusters, outliers, and trends that may not be apparent in the original dataset. Additionally, SOMs provide a means of dimensionality reduction, enabling the representation of high-dimensional data in a more manageable and intuitive manner.
Absolutely. Algorithmic modifications and efficient parallel computing techniques need to be employed to adapt SOMs to big data and streaming data effectively. This will allow researchers and practitioners to make the most out of the potential of SOMs in these challenging scenarios.
Moving on, let's discuss the ethical considerations in the use of SOMs. Ethical considerations play a vital role, especially when it comes to data privacy and potential biases in the training process.
Yes, that's an important point, Avery. SOMs often involve the use of large amounts of personal or sensitive data, which raises concerns about privacy and security. It's crucial to ensure the protection of individuals' privacy and the security of their data when using SOMs.
Absolutely. Additionally, the training phase of SOMs requires carefully selected and representative datasets to ensure unbiased and fair outcomes. This raises ethical concerns regarding the potential reinforcement of existing biases if the training data is not diverse and inclusive enough.
That's right. Ethical considerations should be taken into account when utilizing SOMs to ensure fairness in outcomes and prevent the reinforcement of biases. This highlights the need for responsible and thoughtful use of SOMs in various applications.
Absolutely, Theo. Now let's recap the importance and versatility of SOMs. They are powerful, unsupervised learning techniques widely employed for data visualization and dimensionality reduction tasks.
That's correct. SOMs organize high-dimensional data into low-dimensional representations through a process of self-organization. They work based on competitive learning where neurons compete with each other to become the best representative of the input space.
And by adjusting their weights iteratively, these networks create a topological map that preserves the underlying structure of the input data. This makes SOMs valuable tools in data analysis and exploratory data mining.
Absolutely. SOMs have been successfully applied in various fields, such as image processing, pattern recognition, and clustering. Their ability to uncover hidden relationships in high-dimensional datasets aids in decision-making processes and understanding complex systems.
That's right. And their ability to handle large datasets efficiently and provide topological representations makes them a popular choice among researchers and practitioners alike.
In conclusion, SOMs are a powerful tool for visualization and analysis of complex data. They offer advantages such as preserving the topology and relationships between data points, as well as providing a visual representation of data clustering.
Absolutely. Their versatility and importance have been showcased in various fields of study and applications, such as marketing research, image analysis, and speech recognition.
To fully unlock the potential of SOMs, Challenges related to computational complexity, adapting to big data and streaming data, and ethical considerations need to be addressed.
That's correct, Theo. And while SOMs have their limitations and can be sensitive to parameter choices, their ability to reveal patterns and structures in data makes them an invaluable tool for data exploration and understanding.
And looking towards the future, SOMs hold immense potential in advancing various fields. With further advancements in technology and computational power, we can expect even greater insights and applications from SOMs. That's right. But it's important to note that while SOMs have their strengths, they also have limitations. They can be sensitive to initial conditions, and careful interpretation is needed when analyzing the results. However, with further research and refinement, SOMs have the potential to continue revolutionizing data analysis and visualization in various fields.
Absolutely, Theo. The working principles of SOMs are fascinating. They operate based on several fundamental principles. First, they employ unsupervised learning, where the network learns from the input data without explicit labels or targets. Second, SOMs utilize competitive learning, where each neuron competes with others to best represent a specific input pattern.
Third, SOMs exhibit adaptive learning, as the connections between the neurons adjust based on the input patterns. This allows the network to learn and adapt over time. Lastly, SOMs demonstrate neural plasticity, meaning they can adapt and reorganize as new information is presented to them. These working principles together enable SOMs to effectively organize and visualize complex, high-dimensional data in a simplified manner.
Absolutely. Now let's talk about the neural network architecture of SOMs. It consists of three main layers: the input layer, the layer of competitive neurons, and the output layer. The input layer receives the data points as input, which could be numerical or categorical.
The layer of competitive neurons is where the magic happens. These neurons are arranged in a two-dimensional grid, and each is associated with a weight vector. They compete among themselves to determine which neuron best represents the input pattern.
And finally, we have the output layer. This layer provides a visualization of the learned representations through a grid of nodes. Each node in the grid represents a specific feature or cluster. This hierarchical structure allows SOMs to effectively capture complex relationships and organize high-dimensional data into a low-dimensional representation.
Absolutely, Avery. And that wraps up our discussion on self-organizing maps. We've learned how they work, why they're important in various applications, and their history and development.
Join us next time as we dive deeper into the applications of SOMs and explore real-life examples of how they have been used.
That's right, Avery. But before we move on, let's recap some of the main points from the article.
Sure. Let's start with the nodes and weights in a self-organizing map, SOM. Each node represents a prototype or a specific feature of the input data. These nodes are arranged in a grid-like structure and interact with the input data through a set of weights. The weights determine the similarity between the input data and the nodes, which is measured by a distance metric like Euclidean distance.
Right. And through this mechanism, SOMs can map high-dimensional input data onto a low-dimensional grid, effectively organizing and categorizing the data based on their similarities.
Exactly. And one of the fundamental techniques used in SOMs is competitive learning. It aims to find the best matching unit, BMU, within the SOM network by updating the prototypes in an unsupervised manner. It fosters competition among neurons by adjusting their weights based on their similarity to the input data.
And on the other hand, cooperative learning encourages neighboring neurons to adapt their weights based on the BMU, promoting the formation of clusters within the SOM network. These approaches together create topographic maps that preserve the spatial relationships of the input data.
That's right. Topology preservation is another key advantage of SOMs. It means that the spatial relationships between data points are maintained in the map formation process. By preserving topology, SOMs allow for a better understanding and visualization of the relationships between different data points.
And what's interesting is that SOMs can classify data without any prior knowledge or labeling. They automatically identify clusters or groups within the data set, making them useful in exploratory data analysis. This property allows researchers or analysts to uncover hidden structures within large and complex data sets.
Absolutely. And the versatility of SOMs leads to various applications across different disciplines. In biology and medicine, SOMs can analyze gene expression patterns, predict protein structures, and aid in drug discovery. In finance and economics, they can analyze stock market data, predict market trends, and assess risk factors.
And in environmental science, SOMs can analyze climate data, monitor pollution, and predict natural disasters. In pattern recognition, SOMs can classify images, recognize speech patterns, and aid in handwriting recognition. In social science, they can analyze social networks, evaluate consumer behavior, and predict voting patterns.
It's impressive how SOMs can be applied in so many areas. Clustering and data visualization are also crucial components of SOMs. Clustering involves grouping similar data points together based on their characteristics and patterns. Visualization is the graphical representation of the clustered data, enabling researchers and users to gain insights through visual exploration.
And pattern recognition and classification are key areas where SOMs excel. By exploiting the topological properties of SOMs, patterns within high-dimensional data can be efficiently compressed and visualized. Additionally, SOMs offer a means of classifying unlabeled patterns through winner-takes-all competition.
That's right. It allows for the automatic identification and categorization of data based on its similarity to existing patterns. And that's why SOMs have become indispensable in various applications like image processing, speech recognition, and bioinformatics.
Absolutely. So, in conclusion, self-organizing maps are powerful tools for organizing and categorizing complex data based on their similarities. Their ability to preserve topology and classify unlabeled data make them versatile and useful in various fields.
Yes, they have applications in biology, finance, environmental science, pattern recognition, social science, and more. So if you're interested in exploring data analysis and visualization further, SOMs are definitely worth looking into.
That's right. One of the main applications of SOMs is in image and speech analysis. In image analysis, SOMs can be trained to classify and categorize images based on their visual features such as colors, textures, and shapes. This could be useful in tasks like object recognition, image retrieval, and image compression.
Similarly, SOMs can be employed in speech analysis to recognize and classify spoken words or phonemes. By organizing input data into clusters, SOMs can effectively capture the underlying structure of images and speech patterns, enabling more efficient analysis and recognition in these domains.
Another important application of SOMs is in recommender systems and personalized marketing. Recommender systems use SOMs to analyze and categorize vast amounts of data, creating a visual representation of customer preferences and behavior patterns. This helps businesses understand and predict customer decision-making processes, leading to more effective targeted marketing efforts.
Absolutely. By utilizing recommender systems with the help of SOMs, businesses can provide customers with customized product recommendations and personalized experiences. This enhances customer satisfaction and loyalty, ultimately optimizing business outcomes and improving customer relationships.
Moving on, SOMs also play a crucial role in bioinformatics and gene expression analysis. With the exponential growth of omics data, such as genomics and transcriptomics, there's a pressing need for robust data analysis methods. SOMs have emerged as a popular approach in this field due to their ability to uncover hidden patterns and cluster genes based on their expression profiles.
That's right. By utilizing SOMs, researchers can gain insights into gene interactions and their roles in specific biological processes. Moreover, SOMs facilitate the integration of diverse omics data, allowing for a holistic view of the molecular mechanisms underlying disease and development.
To evaluate the performance of self-organizing maps, SOMs, in various applications, several studies have been conducted. For example, a study by Colhonen used 32 prototype patterns to examine how well SOMs can approximate different areas of the input space. The results showed that SOMs were able to effectively organize these prototypes and capture the underlying topological structure of the input space.
Another study by Lappalainen explored the performance of SOMs in the classification of handwritten Arabic numerals. The findings demonstrated that SOMs achieved high accuracy rates, showcasing their capability to successfully recognize and classify different patterns. These studies highlight the versatility and effectiveness of SOMs in solving real-world problems.
Now let's discuss some of the advantages and limitations of SOMs. One of the key advantages is that SOMs provide a simplified representation of complex data, making it easier to interpret and understand. Additionally, SOMs can handle large data sets efficiently while preserving the topological relationships between data instances.
That's right. Another advantage is that SOMs can perform unsupervised learning, eliminating the need for labeled training data. This makes them particularly useful when working with unlabeled or unstructured data. Additionally, SOMs are robust against noise and outliers, providing reliable results even in the presence of noisy or incomplete data.
However, it's important to note that SOMs also have limitations. They require careful selection of parameters, such as the number of nodes and learning rate, to ensure accurate representations. Moreover, SOMs may exhibit low flexibility at adapting to dynamical environments or rapidly changing data streams.
That's a good point. While SOMs are powerful tools, they do have their constraints. It's important to consider these limitations when applying them to different domains and data sets.
Absolutely. So if you're interested in data analysis and visualization, self-organizing maps are definitely worth exploring. Their ability to organize and categorize complex data based on similarities can provide valuable insights and help solve real-world problems.
Whether it's in image and speech analysis, personalized marketing, or bioinformatics, SOMs offer a versatile and effective approach to data analysis. They provide simplified representations, handle large datasets efficiently, and allow for unsupervised learning. Just remember to consider their limitations and choose parameters wisely.
That's right. One of the key advantages of SOMs is their ability to handle high-dimensional data. As we know, high-dimensional data refers to data sets with a large number of dimensions or variables that are difficult to visualize. SOMs excel at reducing the dimensionality of such data, making it easier to analyze and understand.
That's correct. By transforming high-dimensional data into a lower-dimensional space, SOMs can capture and visualize the underlying patterns and relationships within the data. This not only allows for a better understanding of the data, but also facilitates the identification of clusters or groups. And this makes SOMs extremely useful in various fields like data mining, pattern recognition, and machine learning.
Absolutely. Another important aspect of SOMs is their ability to provide a visual representation of complex data structures. SOMs use a grid-like structure where each node represents a potential grouping or cluster within the data. By mapping high-dimensional data onto this grid, SOMs can reveal the underlying structure and relationships between different data points.
And the best part is that these visualizations are intuitive and easy to interpret. Researchers can gain insights into complex patterns and trends simply by observing the resulting visualizations. This makes SOMs an effective tool for data exploration and hypothesis generation, enabling informed decision-making based on the observed patterns within the data.
Absolutely. And let's not forget about the robustness of SOMs against noisy data. Unlike other clustering techniques, SOMs can handle data sets with missing or noisy entries without compromising their accuracy. This is possible because of the unsupervised learning process of SOMs, where the network adjusts its weight vectors dynamically to form a low-dimensional representation of the input space.
That's right. Noisy or missing data points are still mapped to their respective regions in the SOM, aiding in visualizing and identifying patterns in the dataset even in the presence of noise. This robustness further highlights the versatility and effectiveness of SOMs in data analysis.
Absolutely. However, we have to acknowledge the limitations of SOMs as well. One limitation is their dependency on the initial random configuration of the network. Different initial configurations can lead to different final maps and interpretations of the data. So it's important to be aware of this potential variability.
Definitely. Another limitation is that SOMs are not suitable for handling highly complex and large datasets due to their extensive memory requirements. So it's important to consider the size and complexity of your dataset before deciding to use SOMs.
That's a great point. Additionally, SOMs are prone to overfitting, where the network becomes too specific to the training data and doesn't generalize well to new, unseen data. So it's crucial to be cautious about overfitting when using SOMs.
Absolutely. Another drawback of SOMs is the lack of interpretability of the resulting maps. While SOMs are great for visualizing and clustering high-dimensional data, the units within the map don't have a direct correspondence with the original data dimensions. This can make it challenging to understand the underlying patterns and relationships within the data.
That's right. And it's important to note that the training process of SOMs is unsupervised, meaning there is no target variable guiding the learning process. As a result, resulting maps may capture underlying structures that are not meaningful or useful for the given problem, further complicating the interpretation process.
Absolutely. And finally, we need to consider the dependency on the initial configuration and parameter settings when using SOMs. The initial configuration of a SOM greatly impacts its performance, as the map organizes itself based on these initial prototype vectors. So careful selection and tuning of the initial configuration and parameter settings are crucial for maximizing the effectiveness of SOMs.
That's a great point, Avery. It's important to understand that the performance of SOMs can be greatly influenced by these initial choices. So researchers and data analysts need to invest time and effort into setting up the SOM appropriately.
Absolutely. So if you're interested in using self-organizing maps for your data analysis and visualization tasks, make sure to consider their strengths, limitations, and parameter settings. It's a valuable tool that can provide valuable insights into complex datasets.
Definitely, Avery. Now, one of the main challenges with using SOMs is their computational expense, especially when dealing with large datasets. As the dataset size increases, the time required to train the SOM becomes a bottleneck. This can hinder the quick analysis of large datasets and impede real-time applications.
That's right, Theo. The high computational cost is due to the SOM's mechanism. During the training phase, each data point needs to be compared with all the nodes in the map. As you can imagine, this can become computationally expensive when dealing with vast amounts of data.
To overcome this challenge, efforts have been made to optimize and parallelize SOM computations. One approach is to use parallel computing platforms, which can distribute the workload across multiple processors or machines. This can significantly speed up the training process and enable quicker analysis of large datasets.
Another approach is to adapt the SOM algorithm to exploit the potential of high-performance machines. By making use of specialized hardware or optimizing the algorithm's implementation, researchers have been able to reduce the computational cost of SOMs for large datasets.
Absolutely, Avery. Now let's talk about what makes SOMs so powerful and widely used in various fields. SOMs are a type of artificial neural network that utilize unsupervised learning to group similar data together and map it onto a two-dimensional grid.
That's correct, Theo. This clustering technique allows for the visualization and interpretation of high-dimensional data by representing it in a lower dimensional space. This is particularly useful when dealing with complex datasets that would be hard to grasp in their original form.
And it doesn't stop there, Avery. SOMs not only identify relationships between various data points, but can also classify new, unseen instances. This makes them incredibly versatile for tasks such as image analysis, data mining, and pattern recognition.
That's right, Theo. The ability of SOMs to classify and recognize patterns has led to their widespread use in fields like customer behavior analysis in online shopping. By grouping customers into segments based on their preferences and purchase history, companies can develop targeted marketing strategies.
Absolutely, Avery. And let's not forget about the field of medicine, where SOMs have been used to classify and identify patterns in various diseases. This aids in accurate diagnosis and treatment.
Now let's dive into some real-world examples of how SOMs have been applied in different domains. In the healthcare sector, SOMs have been utilized to analyze medical data, such as electrocardiogram signals. By doing so, they can predict heart disease and help with diagnosis.
That's a great example, Avery. In the finance industry, SOMs have been employed for fraud detection. They can identify suspicious patterns and anomalies in transactions, helping to prevent fraudulent activities.
And in the realm of social media analysis, SOMs have proven to be advantageous. They enable the classification and recommendation of products or content based on user preferences and behaviors, enhancing the user experience.
Absolutely, Avery. These real-world applications highlight the versatility and effectiveness of SOMs in different domains. They underscore the significant impact that SOMs can have on various industries.
Now let's talk about how SOMs were used in these cases and the outcomes achieved. In a study on customer segmentation, SOMs were used to identify distinct customer profiles based on their purchasing preferences. This led to targeted marketing campaigns and increased customer retention and sales.
That's a great example, Avery. Another outcome achieved through the use of SOMs was in the field of image recognition. By training SOMs to identify specific objects within images, more accurate and efficient image classification systems were developed, enabling faster and more reliable data analysis.
Now let's take a step back and understand the basics of SOMs. They are a type of artificial neural network developed by Finnish professor Teuvo Kohonen in the 1980s. SOMs are particularly useful when dealing with complex, high-dimensional data, as they allow for the representation of the input data in a lower dimensional space while preserving the topological properties of the data.
That's right, Avery. This is accomplished through a competitive learning algorithm where each neuron in the SOM is assigned a weight vector that represents a prototype of the input data. The neurons are then organized in a grid-like structure, allowing for the visualization of the relationships between the input data.
As we wrap up our discussion, let's talk about future directions and challenges in the field of SOMs. While they have proved to be a valuable tool for various applications, there are still areas of improvement and research to be done.
Absolutely, Avery. One challenge is developing more efficient algorithms for training large-scale SOMs. The current techniques often suffer from computational scalability issues, and finding ways to overcome this will be crucial for future advancements.
Additionally, integrating SOMs with other machine learning methods could provide enhanced capabilities and more comprehensive data analysis. The combination of different techniques can lead to more powerful models and better insights.
And let's not forget about the interpretability of SOMs. It's important to further investigate how to interpret and understand the results produced by SOMs. This will ensure their practical usability in real-world scenarios.
Finally, there are still challenges related to designing optimal SOM architectures, determining appropriate input representations, and handling high-dimensional data. These research problems need to be addressed to fully unlock the potential of SOMs.
Absolutely, Avery. Now let's dive deeper into the article and discuss the potential advancements in SOM algorithms and techniques. These advancements have the potential to revolutionize various applications, such as data analysis, pattern recognition, and unsupervised learning.
One potential advancement is the incorporation of deep learning techniques into SOMs. This would allow for the creation of more complex and accurate representations of data. Deep learning has shown great success in handling high-dimensional data, and integrating it with SOMs can further enhance their capabilities.
That's right. Additionally, the introduction of dynamic updating rules and adaptive learning rates can greatly improve the efficiency and performance of SOM algorithms. These updates and adaptations can help SOMs better adapt to changing data patterns and improve their clustering accuracy.
Absolutely. And advancements in parallel computing and distributed systems can enable the application of SOMs to larger and more complex datasets. This means that SOMs can be used to analyze and understand even more extensive amounts of data, expanding their usefulness and capabilities.
It's exciting to see how these continuous advancements in SOM algorithms and techniques hold great promise for the future of machine learning and artificial intelligence. The potential impact they can have on various fields is truly significant.
Definitely. Now let's shift our focus to the challenges in adapting SOMs to big data and streaming data. One significant challenge is the computational complexity associated with processing large amounts of information.
Right, Avery. Since SOMs rely on an iterative learning process, the size and dimensionality of the data can significantly impact the efficiency of the algorithm. Handling big data requires algorithmic modifications and efficient parallel computing techniques to cope with these challenges.
That's correct. And in the case of streaming data, where new observations are constantly being introduced, maintaining the SOM's topology can be difficult. Ensuring accurate clustering in such dynamic data requires algorithmic modifications and efficient parallel computing techniques as well.